Now, our next topic is very interesting. It's motion of a charged particle. Motion of a charged particle, let's say plus q. Motion of a charged particle in a magnetic field. That is, if we have a static charge, we are concerned with electric field, but when the charge is moving, what we are concerned with is magnetic field. It will create magnetic field and it will exert or experience a force in a magnetic field. So try to understand this. Let's say we have a magnetic field like this. This is cross sign. This means, I think you must be knowing this. This means the direction of the magnetic field is into the wall. This is the direction of the magnetic field. So we have a magnetic field like this. Let's say let its strength be B. This is our magnetic field B. Now, if we have a charge at this point, plus q charge, moving in this direction, the direction of the velocity is this. What will be the magnetic force due to the magnetic field experienced by this charge? This will be q v cross b. These are vectors, this you know. Now, magnetic field is in this direction. See, sorry, magnetic field red, this is this direction, and velocity is in this direction. What will be the direction of the force? V cross b, that is upward. So the direction of force will be this. Force will be in this direction. Okay, now consider this charge at this point. Velocity is in this direction. So this is like this, magnetic field like this, and this is like this. See, so V cross B, that is to this side, force will be in this direction. So force is in this direction. Now if you try to understand it, force is towards certain point which can be understood as the center of a circle. This can be understood as the centripetal force. That is, your charge will start moving in a circular motion like this. At each point, the force is centripetal towards the center. See, here it will be like this, here it will be like this. So F is actually, and V cross B, this is VB sine theta, theta is 90, so this will be QVB, the magnitude will be QVB. So essentially this force is actually equal to the centripetal force, and if the mass of this charge is m and velocity is v, this mv square by r, where r is the radius. This is centripetal force, so you can equate it QVB. Okay, again I am coming to the conceptual part. Magnetic field is in this direction, so if the velocity is in perpendicular to this, you have a force which is centripetal force, which essentially gives a circular motion to the charged particle. That is, the charge will start to move in a circular motion. What will be the radius of that circle? That we can find after equating this. mv square by r is equal to qvb. So v square cancels. What you get is, let's find value for what? Let's find value for r, or mv is equal to qrb. This is the equation. From here, whatever you want to find, you can get mvqrb. Whichever variable you don't have in the question, you can find out. Now, let's do something more. What will be the angular frequency? V is omega r. Therefore, omega, that is your angular frequency, will be v by r. V is qb by m, qrb by m. So it will be qb by m. From here this, and angular frequency is equal to 2 pi nu. We write it like this. This is frequency, or if you have confusion nu and v, let's use f. So from here f is the frequency of oscillation is 1 by 2 pi qb by m. Okay, so we have so many expressions. Also we can find out the time period. Time period means what time it will take to complete one circle. So t is given by 1 by f. So what you get is 2 pi m by qb. So now you know what is the time period of one loop, completion of one circle. Clear up till now? Now what we'll do, we'll just just complicate the matter a little bit. What happens is, this is the case when magnetic field and velocity are exactly at 90 degrees. We have a circular motion. What if this is not 90 degrees? Let's say, for your understanding, I am showing like this. Let's say this is like this or this. That is, if it is like this or this, we have two components of velocity. One will be parallel to this and one will be parallel to the magnetic field. See, this and this. Now, that which is parallel to the magnetic field, that won't experience force due to magnetic field, because VB sin theta, theta is 0, so magnetic force will be 0. So, if let's say velocity is V and this is V perpendicular and this is V parallel. So, what happens, because of V perpendicular, we have circular motion. That is, let's show it like this. If velocity is this and we have two components, one component is V perpendicular, let's denote it like this, and the other component is V parallel, whatever be the angle, okay, like this. So V perpendicular will be responsible for circular motion, and since we have a component in the direction of the magnetic field, what happens? The charged particle moves in this direction also with a velocity of V parallel. That is what happens. Instead of circular motion, we have circular motion plus motion in this direction. That is, if I start from here, it will be like this. That is, because of V not completely perpendicular to B, we have two components of velocity, one which is perpendicular. This is responsible for the circular motion. So let's say V perpendicular, we use the term V perpendicular here. And because of this V parallel, which is, let's say, in this direction, we have motion in this direction only. So circular motion actually changes to helical motion. It is like this, a helix. So now let me rub this and show you. It actually has this type of motion. Okay, we have this V parallel in this direction and we have this in this direction, V perpendicular. So because of V perpendicular, we are having circular motion with radius r, and because of this V parallel, we are moving in this direction. So for circular motion, the expressions are this. For helical motion, the distance between two circles, this is called pitch, and this pitch, it will from here to here, it goes, which is called one pitch. That distance is what? V parallel, this velocity into time taken to have one complete circle. Clear? So if it comes, let's say from here it starts, goes up, and by the time it comes down, it is here. So this is one pitch. What will be this distance? Let's say the pitch is given as P. So it will be V parallel into time taken to complete one circle. And what is that? That is this T, time period T. This is the time taken to complete one circle. So this is this into this. So from here we find out what is the pitch of the helical motion. I think this is clear. The concept is clear. Let's solve an example and clarify this. Okay. So let's say the particle is basically your electron. So its mass is given, charge is given, velocity is 3 into 10 to the power 7 meters per second, and the magnetic field is perpendicular, which is 6 into this. We have to find radius, energy, and so on. Very simple. See, first of all, let's find radius. So radius is m into v by q into b from this equation. So m is given 9 into 10 to the power minus 31. Velocity is 3 into 10 to the power 7. Then q is 1.6 into 10 to the power minus 19, and magnetic field is 6 into 10 to the power minus 4. So from here we'll get the value of r. Clear? You can do the mathematics. You'll find this as equal to 28 centimeters. Okay. Now if you want to, since we do not have components in the velocity component, that is component of velocity perpendicular to the magnetic field and parallel to it, so we cannot find the pitch, or we cannot say whether it has a helical path or not. Okay, so R is given. What else? You can find omega qb by m. You can find frequency. You can find time period. Another thing was energy. What is energy? You know, energy is only kinetic energy, half mv square. So half into m is given, and v, velocity, is 3 into 10 to the power 7. So this will be 9 into 10 to the power 14. So you can find out, calculate this and find out what is the energy in joules. Okay, so questions are pretty easy. The concept is important to understand how it starts moving in a circular motion, how it takes a helical path if there is a component of velocity in that direction also. Clear? Now let's see motion of a charged particle in combined electric and magnetic field. This I have told you, if we have electric field and we have magnetic field, the force acting on the charged particle will be vector addition of the two forces. This you know. So this will be like this, Q E plus V cross B. This is the expression. This you know. Okay. So from here we'll see a very important concept, that is called velocity selector. That is, can we design a machine, a system where a charged particle with particular velocity passes through it without deflection, and other than that velocity will be deflected towards, let's say, upwards, downwards, whichever way we want. That is, if we have several charges coming at different speeds, let's say one charge is moving at 5 km per second speed, another at 10 kilometers per second speed, and so on. What we want to let the charge with velocity 20 kilometers per second pass without deflection through a combined electromagnetic field. Is this possible? Let's see whether it is possible or not. See what we do. Let's say our velocity is in this direction, okay, and electric field is in this direction, and let's say this is y, this is x, this is z. Our magnetic field is in this direction, okay, all at 90 degrees. So because of this we have electric field here, this direction. This is your force on the charge, this is your charge. Force on charge in this direction, electric field is in this direction, so force is in this direction. The magnetic field is in this direction. So V cross B, see, V cross B, screw anti-clockwise motion. So this will be in this direction. That is, your magnetic field will be, magnetic force due to magnetic field will be in this direction. Okay. So from here, you know the expression, and because they all are in 90 degrees, so sine theta will be 1. So we have this expression, Q E V cross B. Okay. So what you get is, let E be the magnitude. So this is E, and this will now be minus because this is in this direction, and this is VB simply because sine theta is 1. Clear? So the force experienced on this particle, if the magnetic field is in, let's say this is magnetic field, this is electric field, and the motion of particle is in this direction. So we have electric field, the charge will experience force, electric force in this direction and magnetic force on in this direction. So if these two forces are equal, Fe is equal to Fb, then this will go without any deflection. But if electric field is stronger than the magnetic field, the charge, if Fe is greater than Fb, magnitude of this, so what happens? It will go in this direction. If Fb is greater than Fe, then it will deflect to this side. But if these two are equal, the force on this will be 0. So if we say this is 0, what we get is E is equal to Vb. That is, from here we get V is equal to E by B. That is, we can find, or we can calibrate it in such a way that E by B is equal to V. For example, I told you 20 kilometers per second speed, that is 20 into 10 to the power 3, 20, let's say I have to select 20 into 10 to the power 3 meters per second. Any charge which is moving at this speed should go through it without deflection. Let's say this is a cylindrical container, so this should go without any deflection. So what I'll do, if my magnetic field is, let's say 10 to the power minus 4 Tesla, so obviously E will be, V is 20 into 10 to the power 3 into 10 to the power minus 4 B. So this is what? This will be 200. See, no, not 200. It will be 2. It will be 2. So electric field will be 2 newtons per coulomb. Okay. So this is a velocity selector. This is called velocity selector. That is, we want to pass a charge without any deflection through a certain passage. That is velocity selector. Okay, this was used by J.J. Thomson, and it is widely used to find mass to charge ratio or charge to mass ratio in devices called spectrometer. Okay,